if an object is moving with constant velocity, meaning its velocity is not changing, then its average velocity is just equal to its velocity. If it's always moving at, say, 20 miles per hour, constantly 20 miles per hour, then on average it's moving at 20 miles per hour. And if that's true, then since by definition the average velocity is the displacement over the time, then if the average velocity is equal to the velocity and the average velocity is equal to delta x over delta t, then your velocity must be equal to delta x over delta t. And that's what we call our equation for constant velocity. That describes the motion of an object whose velocity is not changing. We can rearrange this a few ways. Let's say delta x over delta t. Let's multiply both sides by delta t. These delta t's cancel, which lets us rearrange algebraically to solve for delta x. Delta x equals v times delta t. This is in a form that should be pretty familiar. In previous classes, you might have heard this described as the distance equals rate times time equation. Except now we know that this is not distance. Correctly, we call this the displacement. It is the displacement. It's the change in position, not the distance traveled. So the displacement equals rate, and by rate we mean the velocity, to be specific, times time. And by time we really mean the time interval. So a few corrections there to make it look like a proper physics statement. Displacement equals velocity times time interval if the velocity is constant. This equation is not true if the velocity is not constant. Let's rearrange this one more way. Let's say delta x equals v times delta t. Let's divide both sides by the velocity. On this side, velocities cancel, and that lets us rewrite this equation as delta t equals delta x over v. Okay, so here's our constant velocity equation. Here it is rearranged to solve for the displacement when we know the velocity and the time interval. Here it is rearranged to solve for the time interval when we know the displacement and the velocity. All right, let's look at an example problem of sort of medium difficulty with objects moving only at constant velocity. Mr. Nixon here is traveling 88 kilometers per hour. He's 110 meters behind Mr. Kennedy, who's traveling at 75 kilometers per hour. How long before Nixon overtakes Kennedy? How do you know that he's going to overtake Kennedy? Well, his speed is greater than Kennedy's speed. If it says something like this, we can assume he's traveling at a constant velocity, if it doesn't say otherwise. All right, so we know we can use our constant velocity equations. Every time we have a problem to solve, start by drawing a picture. I've got a picture here. We can tell that this is a one-dimensional world they're moving in. There's nothing about different directions, so they're moving in a straight line. So I draw a one-dimensional world. And I'm going to also pick which direction is going to be the positive direction. I'm going to say to the right, usually is our positive direction. Sometimes we'll pick to the left will be positive. I'm going to say to the right will be positive. So I wrote my X over here to show that this way, to the right, is the positive direction. We also are going to need a reference point. So I'm going to say the position where Nixon starts, his starting position, that'll be our reference point. We'll call that a position of 0. Okay. What we need to do to solve this problem, as with all of our problems, is structure our approach to problem solving and our presentation of our results with a system called GUESS. Givens, stating the information that is given to you, the numbers that are known. The unknown, stating the variables that you don't know, not immediately. State the equations you're going to use. Solve those equations algebraically, And then finally, last step is to substitute in the actual numerical values. Save that for the end. Okay, let's see how guess works here. All right, we don't always have to start with G. We can often start with our equations. So our equations here. Well, let's map out the situation a little bit more. We know Nixon starts here, Kennedy starts here. So he starts some position in front of Nixon. Let's give a name to it. We'll call his starting position X sub K for the position of Kennedy when he starts. We're going to give a variable to every important quantity here. And we also know that eventually Nixon is going to catch him. They're going to be moving this way until Nixon catches up. So somewhere over here, we don't know where yet, but Nixon is going to catch Kennedy. We'll call that XF, the final position for both of them. So they're starting here. At some future time, they're going to meet over here. Okay, so our equations. For Nixon's motion, we know he's moving at constant velocity, so we can use this constant velocity equation, delta x equals v times delta t. And let's expand here. Delta x, we know that's his final position minus his initial position. Well, the two moments in time that we're interested in are this starting moment when they're 110 meters apart and the ending moment when they meet together over here. So our final position, Nixon's final position will be here when he catches Kennedy. X final is there, and his initial position, we defined it to be 0, our reference point. So delta x for Nixon is x final minus 0. For his velocity here, let's go ahead and name his velocity v sub n. We're going to give a variable name to it. And let's name Kennedy's velocity v sub k. I draw this arrow to represent Nixon's velocity. I drew it a little bit longer than Kennedy's arrow because we know Nixon is moving faster than Kennedy is. We're giving variable names to everything. Okay, so v here will be vn. That's Nixon's velocity. And we don't know how long it's going to take Nixon to overcome Kennedy, so we can just leave that as delta t. All right, Kennedy's equations. For his motion, we know he's also moving at constant velocity, constant v. So delta x equals v times delta t. I expect you to write out the general equation you're going to be using and also label it, constant velocity, indicating I am using this equation because this is a constant velocity equation, because this is a constant velocity situation. I do want you to put a little label like this next to your general equation. All right, now let's replace these generic variables with the variables that are specific to our problem. Kennedy's delta x, well, his final position will be here where they meet, xf, and his initial position is here where we started. We'd call that xk. So Kennedy's equation says his final position where they meet minus his initial position where he started ahead of Nixon equals his velocity, velocity of Kennedy, we're going to call it, times delta t. Notice no numbers here. We're saving the numbers for later. All right, actually, let's just do those numbers right now. We'll go with our givens. Now that we've named each of our variables, let's write down which of these variables we know right now and which ones we still have to figure out. So going through here, I know Vn, Nixon's initial velocity, it's given to us in the problem, 88 kilometers per hour. All right, that's not in SI units. We're going to have to convert it. No problem. We know that there's 1,000 meters in a kilometer, and we know that in 1 hour there are 3,600 seconds. Let's see, did I set that up right? Hours cancels hours, kilometers cancels kilometers, leaving us with meters per second. Excellent. Okay, multiply that through, and that comes to be about 24 meters per second. We're not going to round until the very end, so I'll keep a bunch of decimal places there. 24.444 meters per second. All right. What else do we know of our variables here? Oh, the velocity of Kennedy. We know that Vk is, from our problem, 75 kilometers per hour. All right, let's convert that. In your givens part of the problem solving, this is where you convert all of your numerical values into SI units if they're not already. Cancel like units. And Kennedy's velocity comes out to 20.833, etc. meters per second. That's obviously not the right number of significant figures because this was 75 right here, but we'll keep these extra digits for now and round to the right number of sig figs at the end. Okay, what else do we know here? Kennedy's initial position. Our problem tells us that he started 110 meters in front of Nixon. So xk right there, this distance is 110 meters. So xk is 110. Starting position of Kennedy. That's already in SI units, meters, so we're good there. That's all of our givens. That's all the information that we know from the start. We had 3 numbers in the problem, so that's 3 givens. Unknowns. In this equation, we don't know the final position. We don't know yet where they're going to meet. So let's list the unknowns. And we also don't know, delta t, how long it's going to take them to meet. The change in time from the starting moment to the ending moment when they meet. That's our delta t. Okay, explicitly identifying our unknowns. Now we come to the solve part. Let's rewrite our 2 equations down here. Let's put them together. xf final minus 0 we can drop is Vn times delta t, and let's rewrite this one down here. X final minus xk equals Vk times delta t. Put a little bracket around there because what we've got here is a system of equations. 2 equations with 2 unknowns. That's an unknown, that's an unknown. 2 equations with 2 unknowns. We're going to solve this entirely algebraically before putting any numbers in. All right, well, let's see. I want to get rid of one of these 2 unknowns. Looks like it's easy to get rid of x final because I already know that x final equals this. So I can substitute Vn times delta t in for x final right there. So Vn times delta t. I substituted this in for x final, and now that second equation becomes Vn times delta t minus xk equals Vk times delta t. I'm going to proceed with the algebra step by step here. First thing, I'm going to add xk to both sides. So I have Vn times delta t equals Vk times delta t plus xk. All right, I'm trying to solve for delta t. Remember, that's our goal here. That's our other unknown. All right, so I'm going to subtract Vk times delta t from both sides. I'm going to need another piece of paper soon. So that gives us Vn times delta t minus Vk times delta t equals xk. All right, getting closer. I can rewrite that as Vn minus Vk times delta t. If I factor out that delta t equals xk. Now, all right, last step to solve for xt, I got to get rid of this term over here. Divide both sides through by Vn minus Vk. That way that whole thing cancels out, and I'm left with delta t equals xk over Vn minus Vk. And there is our algebraic solution to our problem. Last step then is just to substitute our values in. It's very useful to do all the algebra to get this final equation because now no matter what these numbers are, we know the solution to this situation. We can change up the numbers and still find the time it takes them to meet. This is now a general solution to this particular problem, and we can put in any numbers here to get the result. All right, so substituting delta t is, we know from our givens, let's go back, look at our givens. We know xk is 110, we know vk is 20.833, and we know vn is 24.444. We wrote it down earlier. So xk 110 meters. Vn is that 24.444 meters per second. Note I am writing the units everywhere, always. No naked numbers, no numbers without units. Minus 20.833 meters per second. All right, punch that into the calculator. Meters divided by meters per second is going to give you seconds. Now we can round it to the correct number of sig figs, which is to 30 seconds. It's going to take 30 seconds for Nixon to overtake Kennedy. Whoa, I got him.